Okay, number 6 on this sheet, universal gravitation questions. 6 says an artificial satellite which weighs 2 times 10 to the 4th newtons. So with that we can get our mass. So our mass is Fg over g. So 2 times 10 to the 4th newtons over 9.81 meters per second squared. So our mass becomes 2038.74 kilograms. Okay, and then it says it's put into orbit around Uranus. The radius of the orbit is 4 times 10 to the 7th. So this time they're giving us the R of the satellite, not the height. We can just use it exactly as they give us 4 times 10 to the 7th. It says we can't use the mass of the planet, and it wants us to find the period of the satellite. So to find the period of the satellite, we need something else that's going around the same planet. I always use the top moon here. So we're at Uranus. I would use Miranda. So its radius of orbit is 1.3 times 10 to the 5th kilometers. So R of Miranda will be 3, I think, times 10 to the 8th meters. And then we also need its period. And so remember in this chart, the period is given in days, hours, and minutes. So 1 day in 24 hours, so is 24 hours. So 24 hours plus 9, 33 hours. Multiplied by 60 to get minutes, and then add the other 56 minutes to it, and then multiply by 60 to get seconds. And when you do that, you should get 122,160 seconds. Okay, so now once we have that, now we can find the period of our satellite. We know r cubed of the satellite over t squared of the satellite will be equal to r cubed of Miranda over t squared of Miranda. And we're looking for the t squared of the satellite, so I'd cross multiply, and you end up with t squared of the satellite equals r cubed of the satellite, t squared of Miranda over r cubed of Miranda. And now fill your numbers in. So R of the satellite, 4 times 10 to the 7th cubed. The period of Miranda, 122,160 seconds squared, divided by R of Miranda, 1.3 times 10 to the 8th meters, also cubed. And then remember, you have to take the square root here. The hardest part in this unit is getting the squares and the cubes and everything in the right spot, okay? Once you take the square root, you should get 2.085 times 10 to the 4th seconds. Okay, so that's part A. Then part B wants to know what is its orbital velocity. Well, since you now have the period and the radius, I would use V equals 2 pi r over t. So 2 pi times 4 times 10 to the 7th meters over 2.085 times 10 to the 4th seconds. And when you do this, you should get 12,054.13 meters per second. Part C wants to know the force needed to maintain the orbit. So you want Fg or Fc. We can't find Fg though because we would need the mass of the planet and we don't have it. So we have to use Fc equals mv squared over r. The m is the 2,038.47 kilograms we found at the beginning of the question. The v is the 12,054.13 meters per second. And the r was our 4 times 10 to the 7th meters. Don't forget to square your v. And when you do this, you should get 7,405.83 newtons. Okay? Part D wants to know the centripetal acceleration. You can find this a couple of ways. You probably did AC equals V squared over R would be my guess. So 12,054.13 meters per second squared. And the R was 4 times 10 to the 7th meters. And when you do this, you should get an AC of 3.63 meters per second squared. And then the last one, finally, is the mass of the planet. So now that you have everything else, you can use this equation, the Fg, the little g, you can use V. So you can use Newton's version of Kepler's third law. I'd probably use the V one just because it's quick. So V squared is equal to G, mass of the central body, over R. So the mass of the central body will be equal to V squared R over G. So the 12,054.13 meters per second squared, 4 times 10 to the 7th meters, over 6.673 to the negative 11 Newton meters squared per kilogram squared. And if you can type this in your calculator correctly and remember to square your V, you should get 8.714 times 10 to the 25 kilograms. 25 makes sense. It's bigger than Earth, which was 24. Number 7 says a satellite which weighs, again, so which weighs 7,000 newtons, so our mass will be 7,000 newtons divided by 9.81 meters per second squared. And so we get a mass of 713.56 kilograms. Part A. Part B, so it's placed 200 meters above the surface of Mars. So our height, or 200 kilometers, is our height. So 2 times 10 to the 5th meters. So we need the radius of the satellite. So it's going to equal the radius, oops, that should be a small r, the radius of Mars plus the height. So you go back to this chart. You go to the radius of Mars, it's 3.43 times 10 to the 6th. So satellite, 3.43 times 10 to the 6 meters plus our 2 times 10 to the 5th meters. So the radius of our satellite is going to be 3.63 times 10 to the 6 meters. Okay, so we're going to use that now in our question. So part A says the weight. So that's what we just found. Part B, part A says the mass. Part B says the weight in orbit. So you're looking for Fg. And this time it doesn't say that you can't use the mass of Mars. So that means you can. Over R squared. So 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared. Mass of our satellite was 713.56 kilograms. And then again, go to your chart to find the mass of Mars. 6.37 times 10 to the 23. So 6.37 times 10 to the 23 kilograms. And then our R was what we just, 3.63 to the 6th meters. And remember, that's squared. And when you do this, you should get an Fg of 2,301.85 newtons. Okay, part C wants to know gravitational field strength, little g. Easiest way to get little g, it's Fg divided by m. So that 2,301.85 newtons divided by the mass of our satellite, 713.56. And when you do this, you get 3.226 meters per second. Okay. And then the last question wants to know orbital velocity. Well, little g is the same as AC, and AC is equal to V squared over R. So V squared is equal to AC times R. So the 3.226 meters per second squared times your 3.63 to the 6th meters.